Hi, I'm Ramin Mojab. In this lecture, I'm going to talk about the expected value of a random variable. As an introduction, I will talk about Riemann and Lebesgue integrals, and then I will define and explain the concept of expected value and variance. Let's assume that there is a function f of x, which is this function, and you must be familiar with the concept of integral. We want to calculate the area in this region, A and B in this region. Okay. In order to do so, we define a partition on A and B. This partition is xi to xi plus 1 for I from 0 to n minus 1. x0 is A and xn is B, which means that we'll have x1 here, we'll have x2 here, and so on. We'll have, for example, x10 here. And now we define the Riemann sum. You're familiar with this sum. It has this value. Let's say that in this interval a to x1, we choose a point here. We call it x1 star, and the value of the function in this point is f of x1 star, which we have it here, and we'll have this rectangle here. We calculate the area of this rectangle, which is this part, and we'll have also an x2 star here, and we will have a rectangle again here, and so on. We can calculate the area of this rectangle, and when n approaches infinity, we'll have the integral, or the area of this region, which is known as the Riemann integral. We use this notation, integral of f of x, which is the limit of this sum when n approaches infinity. Although Riemann integral is useful, we cannot use that logic and solve all related problems. For example, consider this function. We talked about it. It's Dirichlet's function, and we said that it is equal to 0 almost everywhere. And the problem is that the set of rational numbers and the set of irrational numbers are dense subsets of R, which means that every interval has both rational and irrational numbers. This is important because when we want to select xi star, you should know that when, for example, in this interval, xi plus 1, and we want to select here xi star, we don't know that if it is a rational number or it's an irrational number. If it's a rational number, then we'll have this value. If it's an irrational number, then we'll have 0 here, and therefore the Riemann sum is undefined here for this function. There is another logic that we can use and calculate the area of a bounded region. Let's say that this is the function f of x, and this is a, and this is b, and here we have c, and we have d here, and in other words, we have this function here. Here, instead of partitioning this region or the domain, we'll partition the codomain of this function, and therefore assume that, for example, this is yi plus 1, and this is yi, and therefore yi and to yi plus 1 is a region, is a partition on C and D. And what is the preimage of this partition, or this interval under F? We know that this part, this interval, is a part of this preimage. Let's call it F1. We'll also have this partition f2, and here we have f3, and therefore here ei, which is the preimage of wi, is the union of f1, f2, and f3. Or as another example, if we have the Dirichlet's function, the preimage of this partition or this set under f is the set of rational numbers. And also, since f is b measurable, we have this assumption here. ei is a member of the Borel sigma algebra, which means that the Lebesgue measure of ei is defined. I'm not going into details, and I'm not going to define Lebesgue integral here, but I'm just trying to provide an explanation. Here we can have this sum. It's similar to our previous discussion, and for example, yi star is a point here between in this interval, and we can use it and define some. Here we can define 3 rectangles, and when n approaches infinity, we will have the area of this region. And we'll use this notation f of x d of mu. Here d of mu is the preimage of a small wi, and this preimage is not just an interval, it's a union of some intervals. For example, in case of Dirichlet's function, it's the set of all rational numbers. The concepts of a measure and Lebesgue integral are related to each other. Before I explain this relationship, note that I will use this notation for an indicator function. If x is a member of A, then the value of function is 1. Otherwise, it is 0. Now, the measure of A, in which A is a measurable set, equals this integral, the Lebesgue integral of the indicator function over A. For example, assume that mu is Lebesgue measure and A is an interval, A and B. Here, this integral is the area of this region. If this is y equal 1, and this is A, and this is B, then that integral is the area in this region. And as you can see, this is B minus A multiplied by 1, and which is the length of this interval, or is the Lebesgue measure of A. Okay, we have another notation here. If this integral, the Lebesgue integral of the absolute value of f is defined, then we say that f is mu integrable. Note that f is measurable. Here, if this integral is defined, we say that it is also mu integrable, and it is denoted by f as a member of L1. If the Lebesgue integral of f squared is defined, then we say that f is mu squared integrable, or f is a member of L2. I have listed some properties of the Lebesgue integral. If we have this measure space and f and g are mu integrable real functions and a and b are measurable sets, then we can say that the Lebesgue integral of Cf, in which C is a real number, is equals C Lebesgue integral of f. Here, the Lebesgue integral of sum of f and g is the Lebesgue integral of f plus the Lebesgue integral of g. And the Lebesgue integral of f over a equals the Lebesgue integral of this indicator function multiply f over omega. Here we have omega as the sample space. If f is 0 almost everywhere, then the Lebesgue integral of f is 0. If f is less than equal or less than g almost everywhere, then f is the Lebesgue integral of f is also equal or less than the Lebesgue integral of g. And if f and g are almost everywhere equal, then the Lebesgue integral of f equals the Lebesgue integral of g. And if the intersection of a and b is empty, then the Lebesgue integral of f over this union, the union of a and b, equals the Lebesgue integral of f over a plus Lebesgue integral of f over b. And if a is a subset of b, then the Lebesgue integral of f over a is less than the Lebesgue integral of f over b. And if the measure of a is 0, then the Lebesgue integral of f over a is also 0. The expected value of a random variable is simply the Lebesgue integral of that random variable. To be more exact, let x be a random variable with values in this probability space, and let x be p integrable, and its expected value is the Lebesgue integral of x over omega d of p, and we use this notation e of x for the expected value of x. Right now it's not easy to explain the logic behind this formula. That's why I will try to explain this equality first, and then I will explain the logic behind this definition. I try to explain why this equality holds. First of all, we should divide x into two parts, x positive minus x negative, and in which x positive is the maximum value of x and 0, and x negative is the maximum value of 0 and minus x. Now we have x plus as a function of w equals 0 to x plus d of x, and we can say that since we can use an indicator function and say that this is from 0 to infinity 1 in which x is less than x plus of w. This is the indicator function d of x, and since x plus here, note that if x is greater than x plus, then the value of this indicator function is 0, and that's why we use an infinity here instead of x here. And we can omit this positive sign here because x is positive. The integral is from 0 to infinity, and therefore this is the integral 0 to infinity 1x less than x d of x. Now we assume that the expected value of x plus is less than infinity. If this is infinity, then the integral or the expected value is whether infinity or it is undefined. And the expected value by substitution, we have the integral over omega, this part 0 to infinity, the indicator function x less than x d of x d of p, and we can use the properties of the Lebesgue integral and show that this is equal to the integral of the probability that x is less than x and d of x. And this is the first part of this equation. 1 minus this is 1 minus the cumulative distribution of x. We can follow the same procedure and prove a similar formula for the expected value of the x minus for the second part of this equality. What is the logic behind the definition of the expected value? Assume that x is a positive random variable, and therefore the expected value of x is this integral. We know that this integral is the integral of these probabilities. X is greater than x d of x. Since this is an integral of probabilities, we can say that the expected value of x is the sum of all elements of this matrix, because, for example, the first column, the sum of elements of the first column is the probability that x is greater than 0. The sum of elements of the second column is the probability that x is greater than dx. dx is a very small number. The third column is x, the probability that x is greater than 2 times dx, and so on. And therefore the sum of all these probabilities is, we can say that it's the integral that we talked about here. Okay, now consider the rows of this matrix. The first row is the probability that x is in between 0 and a very small number, d of dx. The second column, the second row, we have the probability that x is between dx and 2 times dx, and we have two of these probabilities. In the third row, we have 3 probabilities, and each of them is the probability that x is between 2 dx and 3 times dx, which means that as the value of x increases, or as this interval moves forward, the importance of the probabilities, or the importance of the value of x, increases too. Of course, I know that this explanation might be inadequate. That's why in the next lecture I will talk about the classification of the random variables, and there we will talk about continuous and discrete random variables, and I can provide a better explanation there. We can use this formula and prove this one. In order to prove this, we need Riemann integral. You might be familiar with this integral. The integral from a to b, f d of g equals f of b g of b minus f of a g of a, minus the integral from a to b g d of f. And we should use this formula and expand this part and this part. Here we will have two limits: limit of x 1 minus the CDF of x, and we'll have, when x approaches infinity, and we'll have x f of x, the CDF of x, when x approaches minus infinity. This is here, this is my infinity, and this is 0, and here this is minus infinity, and this is 0. And these two limits are cancelled out by each other when we expand these two parts. We can define the concept of the variance of a random variable. Let x be a random variable which is p-squared integrable. This means that e of x is defined and e of x squared is also defined. The variance of x is the expected value of x squared minus the expected value squared of x. We can prove some equalities here. For example, let x be a random variable and a and b be two real numbers. Here, the expected value of ax plus b equals the a plus the expected value of x plus b. We can use one of the properties of the Lebesgue integral and easily prove this equality. Here we have another formula for the variance of x, and in order to prove this, note that x2 plus the e2 of x is equal to x minus e of x squared minus 2 times x e of x. You can use this equality and prove that this formula is valid. And we have another equality here. Variance of ax plus b is equal to b squared variance of x. Again, we can use the definition of the variance and one of the properties of the Lebesgue integral. Thanks for your time. My next lecture is about mass and density probability functions.